This is basic electronics engineering. The paper code is EC201. It has 3 number of lectures. Total contact hour is 36 and the total credit is 3. Myself, Dr. Indranath Shakar, Associate Professor, Department of Electronics and Communication Engineering at JS College of Engineering, Kolleri. Welcome to Module 2 of PN Junction Diode and its applications. There are 4 course outcomes of this subject. The first course outcome is to study the PN junction diode, ideal diode, diode models and its circuit analysis, applications of diodes and special diodes. Basically, our focus is to develop the growth of the students' knowledge on the foundation construction of the PN junction diode, as well as the different doping concentrations of the diode and the corresponding applications of the diode. So starting from the different model analysis of the diode for application in various types of circuits, we will carry out several mathematical examples which will give immense of knowledge to the students, so that students can play with diode, students can perform projects, create models using the diodes. The second course outcome deals with operational amplifier. Here our main focus is to develop the students' knowledge with the basic internal stages of the op-amp, so that students can freely demonstrate about the working principle of operational amplifier, starting from the basic amplifiers using op-amps such as the inverting and non-inverting amplifiers. Students will be able to create several types of circuits such as the differentiator, integrator, as well as buffer amplifier, instrumentation amplifier, so precision diode. There are various applications of operational amplifiers, and students can just play with op-amp so that they can create several types of projects using op-amp. And thereafter our attention will be towards the positive and negative feedback circuit. Here the students will go through the knowledge of the basic amplifier, and thereafter they will apply the feedback concept to the basic amplifier, so that they can enhance the parameters such as the input impedance, output impedance, bandwidth, gain of basic amplifier to some modified value. So feedback amplifier is another part of the control system which can give the idea of control system subject. The fourth one is dealing with the development and capability to analyze and design the simple circuit containing nonlinear elements such as the transistors, using the concept of load lines, operating points and incremental analysis. In this subject there are 5 modules. Module 1 is the basics of semiconductor, Module 2 is the PN junction diode and its applications, Module 3 deals with the bipolar junction transistor, and Module 4 deals with the field effect transistor. Module 5 is the feedback and operational amplifier. Module 6 is the cathode ray oscilloscope. Now here the chronological arrangement of the subject module will be beneficial for the student to grow the knowledge from basic foundation elements to complex circuitry using the basic electronics subject. The prerequisite of this subjects is the fundamental of electricity, direct current, devices and circuits, series and parallel circuits, to the study of active and passive components, Ohm's law, Kirchhoff's law, and KVL, KCL, Ampere's law, etc. KVL stands for Kirchhoff's voltage law and KCL stands for the Kirchhoff's current law. The course outcome, program outcome mapping is having several weightage depending on the high, medium and low, which are numerically weighted by 3, 2 and 1. We have an explanation of such course outcome versus program outcome, because program outcome is assigned by National Board of Accreditation. There are 12 program outcomes which are mapped to the course outcome. Now the first course outcome, as we have gone through, it is the study of PN junction diode, ideal diode, uh, diode models, its circuit analysis, its applications, as well as special diodes. The weightage has been given maximally to the program outcome 1 and program outcome 12. The program outcome 1 states that it applies the knowledge of mathematics, science and engineering fundamental and an engineering specialization to the solution of complex engineering problems. Similarly, program outcome 12 deals with the part, the lifelong learning, in which it is stating that recognize the need for and have the preparation and ability to engage in independent and lifelong learning in the broadest context of technological change. So as the basic foundation knowledge of this course outcome 1 which it dealt with, that is why it is mostly matching with program outcome 1 and program outcome 12, and there are medium weightage given to program outcome 2, 3, 5 and 11. Now the second program outcome is the problem analysis, and the third program outcome is the design and development of solutions, and the fifth one is the modern tool uses, and correspondingly 11th one is the project management and finance. So therefore these program outcome statements are getting the middle weightage, that means numerically 2 it is given. And the fourth program outcome is the conduct investigations and complex problems. Since we have minimum concept of start of the complex problem in this subject, because there is another advanced course, analog electronics, the students will go through in the fourth semester. They will be understanding in more detail, so that is why complex problems will be suitable in the analog circuit subject, not in the basic electronics. The main course objective of this basic electronics is to impart the fundamental knowledge to understand the basics of semiconductor and components like diode, transistor, FET, MOSFET and operational amplifier. It will be it will build mathematical and numerical background for design of electronic circuits and components value. Students equipped with the knowledge and training provided in the course will be able to participate in design and development and operation in the different area of electronic system. So therefore the basic electronics subject is actually, in a nutshell, is the basic knowledge for the several components, so that students can know the characteristics of those foundation components, and knowing the characteristics of the component, students can apply this component for their own project or own circuit development. And during the circuit analysis, student can measure the parametric value of the component, so that they will understand the status of the component, whether it is giving correct value or it is giving the wrong value. So for this subject, a data sheet for individual component is also mandatory for students to see, because until and unless students go through the data sheet, they will not understand the detail of a particular component, because the data sheet gives not only the physical structure, dimensions, as well as various electronic parametric value for each and every component, and there are much more details given in data sheets because it is made by the manufacturer. In today's class, we will discuss the PN junction diode, PN junction formation and the depletion region, built-in potential at PN junction, energy band diagram of PN junction at equilibrium. Now in this figure, it shows that different types of diodes which are intended for different types of applications, the symbolical representation and the actual physical loop. On the left hand side, we are seeing series of symbols are given initially for the normal diode, uh, thereafter Zener diode, Schottky diode, tunnel diode, light emitting diode, photodiode, laser diode, current regulator diode, varactor diode. So these are intended for different types of application. As we know, light emitting diode are very much popular for generation of light, different colors of light which are emitted by applying sufficient amount of voltage. Similarly, the photodiode is used as a receiver that will receive the light and uh, and corresponding circuit operation can be performed. Similarly, laser diode, which emits the laser frequency. Similarly, current regulator diode, which is applicable for the limitation of the current in a specific load. Varactor diodes, in which the capacitors are varied according to the applied voltage. Now here, PN junction diodes, that is, though there are various types of diodes, these diodes are having two terminals. One is called anode, another is called cathode. The direction of the flow of current is shown by the arrowhead. From left to right, the current flows as shown in the symbol. Similarly, the actual loop for the normal diode, which is shown on the left bottom, the larger black region is the anode and the small silver region is the cathode. So anode and cathode should be properly identified from the model available in the market, so that voltage could be applied properly for specific application. The diode characteristics are formed by applied voltage versus current plot. This diode characteristics shows the operating point which is required to be set for a particular circuit operation. PN junction formation and depletion region are the important fact in case of PN junction diode. P-type semiconductor and N-type semiconductor are chemically attached, and thereafter some incident follows. That is, after formation of the PN junction, the P side is having the higher concentration of holes, on the N side high concentration of electrons. So due to the potential gradient, holes are trying to move from P side to N side, and electrons are trying to move from N side to P side. So when the P-type semiconductor and N-type semiconductor were standalone at that time, the acceptor ions are covered by holes and donor ions are covered by electrons under the thermal equilibrium. So under the PN junction formation, when the electrons are trying to move from N side to P side, they uncover those donor ions and the holes are uncovering acceptor ions, and they are crossing the junction. So when they are crossing the junction, these electrons are again occupying the valence band hole positions, and thereafter this is called recombination, and thereafter the immobile charges, that means the uncovered charges, are gathering at the junction, forms the depletion region, also known as space charge region. These space charge region are sufficiently blocking the flow of further electrons from N side to P side and holes from P side to N side. That is why once the space charge region formed, it will block the diffusion of electrons as well as holes. Now in this figure, it is clearly showing that the middle portion, in which the blue acceptor ions and the red donor ions are gathering at the junction of the P-type and N-type semiconductor under the PN junction diode. So they are making the space charge region, which are blocking the further flow of electrons from N side to P side and holes from P side to N side. Also, it is showing the neutral region of the P side and neutral region of N side. That is, under the thermal equilibrium, the P-type and N-type semiconductor are having the holes and electrons which are not moving are not crossing the junction due to the presence of space charge region. But the electric field works from the donor ions to the acceptor ions because donor ions are having higher potential, that is positively charged, and acceptor ions are negatively charged. So therefore, the diffusion of holes or electrons, though it is flowing from the left to right for the holes and right to left for the electrons, the presence of space charge region in which the donor ions and the acceptor ions are uncovered, they exert force in the opposite direction to the diffusion of the charge carrier. That means electric field on holes due to the acceptor ions are from the right to left. That means minority holes which are present in the n-type semiconductor are attracted towards the acceptor ions at the depletion region. Similarly, the electrons which are present as minority carrier in the p side are attracted by the donor ions. So therefore, the electric field on the electron is also from left to right. Now this is the energy band diagram of p-n junction at equilibrium. As we know, p-type semiconductor is having a high density of holes. Therefore, the Fermi energy level comes closer to the valence band because the existence of hole is not in the conduction band but in the valence band. That is why the valence band energy level comes closer to the Fermi level. Similarly, for the inside, since free electrons are plenty, that is why the energy band, that means conduction energy band, comes closer to the Fermi energy level. So it is very clearly shown that why Fermi energy level are closer to the conduction band in case of n-type semiconductor, and it is Fermi level is closer to the valence band energy for the p-type semiconductor. Another thing is very much clear: the drift and diffusion of the holes and electrons, the forces, how it works, very clearly shown. The drift forces are working from left to right at the top for the conduction band, whereas in case of valence band, it works from right to left. Similarly, for the diffusion, the force works from left to right in the valence band, whereas in case of conduction band, it is working from right to left. It is obvious because electrons present in the conduction band are trying to move from n side to p side due to the diffusion, and from p side to n side holes are moving due to the diffusion. So that is why they are converging towards each other for recombination. But the drift force, which is the force due to the presence of the built-in potential at the p-n junction, so since positive ions are present on the n side, so they exert force from right to left. So that is why drift force is from right to left. Similarly, for the p side, the holes are present. So there is also acceptor ions. So acceptor exerts force from left to right. Now here is an important mathematical equation for the width of the depletion region, as it is showing that epsilon Si, this epsilon Si is the electrical permittivity for the silicon. For the germanium semiconductor, we can replace this by epsilon Ge. So the standard value of epsilon Si is 10 to the power minus 12 farad per meter. Another thing is that Na and Nd, that is the acceptor concentration and the donor concentration, are also present in this equation. There is a phi 0, which is the built-in potential, and the Vd means the applied voltage on the diode. So there are two types of diode voltage. One is positive, another is negative. We will see, which is known as transistor biasing. If the diode voltage is positive, that means forward bias, at that time phi 0 minus Vd will be reduced. Therefore, the width of the depletion region reduced due to the applied forward bias voltage. And when the applied voltage is negative, at that time phi 0 minus Vd is increased. So under the reverse bias, we see that width of the depletion region increases. So this is the mathematical expression by which we can explain that under the forward bias, the depletion region width reduces, whereas in case of reverse bias, depletion region width increases. Now, built-in potential at the PN junction can be uh, extremely mathematically shown in this way. First is the drift and diffusion current that we need to know. The diffusion current, as it is shown, uh, which is moving from left to right. Now, why it is shown from left to right? The reason is that the flow of hole from left to right, that is the direction of the current for diffusion. Similarly, for the electron which is moving under the diffusion from right to left, we know the direction of current is opposite to the movement of electron. So therefore, under the diffusion force, the direction of current is also left to right. So therefore, hole current and electron current, the direction is unique from left to right. But for the drift, there is a positive charge on the right side which attracts electrons from left side. So therefore, from left side, minority electrons are attracted towards the donor ion. So therefore, the current direction is from right to left. So drift current is right to left. Similarly, for the holes present in the n side as minority charge carrier are attracted by the acceptor ions. So therefore, minority holes from n side are also moving from right to left. So therefore, the direction of the drift current is clearly explained. The summation of the drift current and diffusion current under the thermal equilibrium, that means without applying any external force or voltage, this summation is zero. Since the drift current and diffusion current summation is zero, therefore their current density, related density means the drift current density and diffusion current density summation is also zero. Now, the expression of drift current and diffusion current mathematically can be given as the product of the charge, the mobility, electric field, and the carrier concentration. So it is for P for the holes and N for the electrons. So here we are considering only for hole. So drift current is given by Q into mu P into capital E into small p, because P is the hole concentration, plus the diffusion current density, which is given by the product of the charge carrier Q, the diffusivity of the holes dP, and the negative slope minus dP dx. Now, why the slope is negative? Because if you see the PN junction, the middle figure on the left hand side, the slope is negative if we move from left to right. So that is why minus dP dx is taken. So these two summation is equal to 0. Therefore, we can easily write mu p into minus dP dx into p is equal to dP into dP dx. So here minus dP dx is taken because the electric field and the electric field is normally equal to the slope of the voltage with negative polarity, because the voltage gradient and the electric field direction is opposite. So ultimately, this mathematical expression calculates the potential which is formed at the junction, known as the built-in potential, which is given by the product K into T, means Boltzmann constant, into ambient temperature under the absolute temperature expression, divided by the charge carrier Q into the natural log of the ratio, where the numerator is the product of the acceptor concentration and donor concentration, and the denominator is the square of the intrinsic carrier concentration. So here one thing we can note is that when we calculate the built-in potential Vx2 minus Vx1, what does it mean? Vx2 means at the right side, x2 is the position where the potential is Vx2, and on the left hand side, x1 is the position in which the potential is Vx1. So these two potential are due to the donor and acceptor, we should remember. And one more thing is that the whole concentration Px1 and Px2. What is Px1? Px1 is the whole concentration on the P side, so it is the majority charge carrier concentration. But when you are telling Px1, Px2, Px2 stands for the whole concentration on the right hand side. Now, what is present on the right hand side? It is the n-type semiconductor. So at n-type semiconductor, Px2 whole concentration is nothing but the minority charge carrier concentration, which can be represented by the ratio of the square of intrinsic carrier concentration and the donor concentration.